Now that you know the basics of OO programming, you're ready to start exploring some advanced OO concepts in this chapter. Let's kick off with the overview. We will start by reviewing annotations. This will be followed by a discussion on overloading methods and the this keyword. We will then zoom into information hiding and class inheritance. Next topics on the agenda are packages and interfaces. The chapter will conclude by discussing garbage collection. Annotations provide metadata about source code. Unlike comments, annotations are inspected and evaluated by the compiler. They always start with the add symbol. We already saw an example of the add test annotation when we discussed JUnit testing in chapter 6. Remember, the add test annotation was used to annotate a test method. Other annotations available in java.lang include add deprecated, add override, and add suppress warnings. Add deprecated is used to indicate that an element, such as a method or class, has been replaced by an improved alternative and should no longer be used. Add override indicates that a subclass is overriding an element from its superclass. We will give some examples of this later. Add suppress warnings instructs the compiler to suppress specific warnings that it would normally generate. Method overloading refers to using the same name for more than one method in the same class. Java can determine which method you are calling as long as the number or type of parameters is different in each method. Here, you can see an example of this with a class book. What do you think will happen if you run this code? Well, it will generate an error saying that the read method is duplicated. Indeed, you have two methods with the same name, read, and neither has any parameters. Let's look at this alternative. Now we have two read methods, one that has no input arguments and one that has one input parameter I of integer data type. To Java, these are two different methods. Method overloading is very handy when you are defining constructors. You can see this illustrated here. Remember, a constructor should have the same name as the class. How many constructors do you see here? Indeed, we have 4 constructors, each with a different number of input arguments. The this keyword is placed inside an instance method or constructor in order to refer to the object whose method is being called. Let's look at this example. We have a class person with a name variable and one constructor with a string input argument. You can read the constructor as the name variable of this person object being constructed should be given the value of the person name string provided as a parameter. The print name method then says, print the value of the name variable of this person object whose method is being called. The this keyword can be handy to avoid ambiguity. For example, when a local variable and an instance variable have the same name. You can see this illustrated here. We have a class person with a string variable name. It has 2 constructors and a print name method. The second constructor has one input argument name. To avoid ambiguity between the instance variable name and the local variable name, you can see that the this keyword has been used. Also note that the first constructor uses the keyword this to call the second constructor with the input argument unknown. Here you can see a more extensive example of method overloading and the use of the this keyword. We define a class person with a name and birth date variable. It has two constructors, each with a different list of input arguments. The first constructor uses the localDate.off method from the java.time package to assign a date variable from the three integer values specified. The second constructor only uses the name as its input argument. The this keyword is then used to call the first constructor with the name specified and the year set to 1900, month to 1, or January, and day to 1 as well. You can also see that the method calculateAge has been overloaded. More specifically, there exist three versions of it. The first method uses the localDate.now method to compare a person's birth date to the current date. Period and period.getYears handle the calculation for you. The second calculateAge method uses a specified date instead of the current date. This could be handy if you would like to know how old a person was when he or she graduated high school, for example. Finally, the third calculateAge method specifies the input date as three integers, one for the year, one for the month, and one for the day. Information hiding, also referred to as encapsulation, is an object-oriented practice that hides the internal representation of objects. The idea is to make member variables private such that they are not accessible from outside the class. This can be accomplished by creating accessor methods to grant access to view or modify the values of the variables. This gives the programmer control over how and when variables are accessed, which contributes to program maintenance. Here we define a class product with three variables: product name, product idea, and product price. We have one constructor which initializes the values for all three variables and a displayString method to print a string representation of the object. The class product program then creates a new product object called myWidget. However, after the product is created, anyone can change the price, even to a price that doesn't make any sense, such as a negative price. An accessor method would be handy to verify that correct values are entered. In case incorrect values are entered, a warning message can be displayed or even an exception raised. Accessor methods are also handy to retrieve values from variables. In our product program, we might create an accessor method that adds a tax or fee to the price before returning the total price. Finally, encapsulation can improve program maintenance by limiting the impact of changes in one class on other related classes. In our product program, you might want to adapt the product class later to accommodate more information about products or to change the representation in some way. However, as long as your displayString still returns a string, the other classes calling this method continue functioning as expected. If every related class printed the statements based on the instance variables directly, a change to the product class would require adaptations to every other class to ensure the printing methods still functioned properly. The first step to restricting access to variables or methods is to appropriately define access modifiers. There are 4 access modifiers that can be applied to methods and variables in Java. Public, which means accessible by any class. Protected, which means accessible by subclasses or classes in the same package. No modifier, which means accessible by classes in the same package. And private, which means accessible only from within the same class. The below table illustrates these access levels. Encapsulation calls for the class or instance variables to be given only private access, meaning they are only directly accessible from within the same class. The access modifiers of your accessor methods can be set according to the demands of the program. For example, you might make an employee's date of birth readable to everyone with a public accessor method, but restrict changes with a private accessor method. The product class might set price changes to package protected, so subclasses of the product and a discounter class in the same package can adjust the price. Getters are used to access variable values for viewing only. You should create a getter method for every private variable. Depending on the access level you want to give to the variable, you can set the access modifier of its getter method. Here, you can see a product class with 3 variables: product name, product idea, and product price. You can also see that a public getter method has been added for each of the 3 variables. Setters are the methods you use to modify or set the values of variables. Just like with getters, you should create setters for every variable. Setters can replace the statements you used to use in the constructor method. You can see this illustrated for a product class. We now also introduce setter methods for each of the 3 variables. The setName method is defined as public, whereas the setIdea method is declared as private. This is because we would like to ensure that a product's idea should not be changeable from outside the class. The method setPrice includes an additional validity check. More specifically, it uses the method isValidPrice to verify if the price is within a certain range as specified by the min price and max price values. If the price is not valid, the setPrice method will throw an illegal argument exception. Here you can see how our product program class has been adjusted. We now use the setPrice method to change the price of my widget. The exception can be caught using the try-catch block we discussed in the previous chapter. What do you think will happen if we run this code? Indeed, since the price is set to -5, it will raise an exception saying java.lang.illegalargumentException -5 is an invalid price. Here you can see another example of information hiding and the use of getter and setter methods. We define a class account with 2 variables, name and amount. A constructor is defined with 2 input arguments for both variables. It calls the corresponding setter methods to initialize both variables and sets the scale of the amount variable to 2 decimal points and round half up for the rounding mode. As you can see, both getter and setter methods have been defined for both variables. The setName method defines a pattern string variable. The matches method is then used to verify that the string contains only letters and numbers without any symbols. This or a similar pattern might be a requirement for an account's name. The access modifier for the setAmount method is set to private, since it will only be used in the constructor. We also included public withdraw and deposit methods to subtract or add funds to the amount. Inside both methods, we check for negative balances to make sure the account is not overdrawn. We can now define an account manager class. It creates a new account object, myAccount, and initializes the amount to 10. Getter methods are called to display both variables of the object. A try, catch, finally block is used to try and withdraw 20 from the account. What do you think will be the output of this? Here you can see the output if we run our account manager class. Since 20 is bigger than the amount 10, an exception is thrown saying invalid withdrawal. The finally statement then prints the amount, which remains unchanged to 10, as you can see. Java classes are organized in a hierarchical inheritance structure. Subclasses are derived from superclasses. A subclass inherits both the variables and methods from the superclass. The class object is the highest level superclass. In other words, it has no parent class above it. All other classes are either subclasses of object or subclasses of object. Inheritance represents an is-a relationship. For example, a student is a person, so the class student is a subclass of the person class. An employee is a person too, so employee could be another subclass of person. An undergraduate is a student, and a graduate is a student, so you can create two additional subclasses of the class student. Staff and faculty might be subclasses of the class employee. To indicate that a class is a subclass of another class, we use the extends keyword in the class declaration, as you can see here. Public class employee extends person. Here you can see the inheritance relationship visualized. Let's ask some questions to see whether you get this. Where would you put the name and birth date variables? Well, I would put them in the person class since every person, no matter if they are a student or employee, has a name and birth date. Both variables can then be inherited by all the subclasses that follow. Where would you define a method is passed? Well, I would put it in the student class, since this method applies to all students, no matter if they are undergraduate, associate bachelor, or postgraduate, master, or doctorate. Where would you include a variable PhD title? Well, this variable can be added to the doctorate class and will not be inherited by any other class. The keyword super allows us to refer to the superclass. It's quite similar to the this keyword discussed earlier. Super is commonly used in constructors to invoke the constructor of the superclass. It is also used to access the variables and methods of the superclass. Here you can see two classes, person and employee. The person class has one variable name, a constructor, and a getter and setter method. Notice the use of the this keyword. The employee class is a subclass of the person class and adds the manager and ID private variables. Notice how the super keyword is used in the first statement of the constructor. It calls the constructor of the person class since an employee should be constructed as a person is constructed. The employee constructor then also initializes the manager and ID variables. The class definition then continues by declaring the getter and setter methods for both variables. Here you can see two methods that we may wish to add to the class definition: display name and display identification. In the former, we use the keyword super to call the getName method of the person superclass. Suppose now that we extend our person class with an ID variable, which we use to uniquely identify people in our database. In other words, an employee now has two IDs, the person ID and the employee ID. To get access to both, we can make use of the super and this keywords as illustrated in the method display identification. Remember that subclasses inherit both variables as well as methods from their superclasses. In other words, if the student superclass has a calculate GPA method, then the graduate and undergraduate subclasses have this method as well. The subclasses can also choose to override the inherited calculate GPA method and provide a more specialized implementation. This is referred to as method overriding. You can see an example illustrated. Let's say the student class has a variable grades, which is an array of student grades. The calculate GPA method then simply calculates the average of the grades, as you can see. Now suppose graduate students only get credit for grades above a certain minimum. For example, only 80% and higher are accepted, and courses with a grade below 80% must be repeated. To accomplish this, the graduate subclass overrides the calculate GPA method by introducing the if statement as illustrated. Note that we also added the add override annotation to explicitly indicate that this method overrides an inherited one. Polymorphism is another key concept in OO programming and states that the same method can be implemented in various ways depending upon the object on which it is invoked. We already spoke about static variables and methods. Remember, both do not require an object but work at the class level instead. Polymorphism applies to objects rather than classes. Static methods can be bound to their implementations at compile time. This is referred to as static binding or compile time binding. Java restricts static methods from being overridden, but they can be overloaded as illustrated earlier. Dynamic binding, also called virtual method invocation, is the binding used for instance methods to allow for polymorphism. In other words, when a method is overwritten, there are multiple implementations that can be called depending upon the object in question. Dynamic binding means that the binding of instance methods to the appropriate implementation is resolved at runtime instead of compile time based on the object and its type. During execution, the Java virtual machine will perform a bottom-up search in the class hierarchy to find the most specific implementation of the method referred to. Here you can see our person example revisited. In the main method of the person program class, we create two student objects, John and Anne. John is a master student and Anne is an associate student. For both objects, we set the grades using the setGrades method. Note that we assume they both have the same grades for all 5 courses. When this Java program is executed, the JVM will perform a bottom-up search for the getName method for John. It will find this in the person class and execute it. Next, it will need to execute the calculate GPA method for John. The master class does not have a calculate GPA method, but the graduate class does. Hence, the JVM will execute this method. For Anne, the same process is followed. In other words, the getName method from the person class is called and executed. For the GPA, neither the associate nor the undergraduate class has a calculate GPA method. So the student version of the method is called and executed for Anne. You can see that the output is different for both objects despite them having the same grades. This is because dynamic method invocation allows different versions of the method to be called depending on the object calling it. As already mentioned, all classes in Java descend from the class object. This class has various methods, which you can see listed here. The clone method creates and returns a copy of an object. The equals method indicates whether two objects are equal. The finalize method is called by the garbage collector on an object when garbage collection determines that there are no more references to the object. We will come back to this later. The getClass method returns the runtime class of an object. The hashCode method returns a hash code representing the object's memory address by default. The toString method returns a string representation of the object and is called when you print the object. All these methods are inherited by every Java class, and except for the getClass method, which is final, can be overridden where necessary. An abstract class is a class which cannot be instantiated. In other words, you cannot create objects from an abstract class. It is commonly used to group variables and methods shared by various subclasses. For example, you might have an abstract class shape with subclasses such as rectangle, circle, and triangle. Every shape should either be a rectangle, circle, or triangle, so it doesn't make sense to create shape objects, and that's why we make the class abstract. Abstract classes can be declared using the keyword abstract in a class declaration, as you can see here. Abstract classes can have both implemented as well as abstract methods. Abstract methods are declared without an implementation. For a shape class, you can see that the calculate area method has been declared as abstract, since it will be implemented differently for a rectangle, circle, or triangle. A class that contains an abstract method must be abstract itself. Abstract methods are also declared using the abstract keyword, but instead of opening curly brackets, the declaration is completed with a semicolon, as you can see illustrated. Here you can see a class circle defined as a subclass for shape. It has two variables, the radius and the constant pi, which is needed to calculate its area. You can see that the method calculate area, which was inherited from the class shape where it was defined as abstract, is overwritten here with an implementation. Packages are a Java construct which work much like folders. They allow to group related classes and offer additional features such as namespace and access control. Several classes can have the same name, as long as they are located in different packages. A package, or specific classes thereof, can be imported using the import statement. In order for a program to identify a package by name, the program should be executed from the directory that contains the package, or the class path environment variable must include the path to the package. The class path environment variable tells the Java virtual machine where to find classes and packages when needed. An interface defines a protocol or contract of behavior. You can think of it as a template for a class, as it specifies what a class must do, but not how to do it. It is declared using the keyword interface, such as public interface followed by the name of the interface. Interfaces contain headings for public methods without implementations. All methods in an interface are abstract. It is recommended to add comments to each method to make clear what it is intended for. Interfaces either have no or a public access modifier. An interface may have variables only if they are final, static, and initialized with a constant value. A class can implement an interface. If a class implements an interface, it must implement all methods defined in the interface. A single class can implement any number of interfaces. Interfaces can extend one or more other interfaces. Similar to superclasses, polymorphism also applies to interfaces. Here you can see an interface measurable. It is an interface for measuring methods. It has two public abstract methods to calculate the perimeter and area of an object. We now define a class shape, which implements our measurable interface. As previously, the shape class is defined as abstract, with one private string variable, color. The circle class is a subclass of the shape class. It has implementations for the calculate area and calculate perimeter methods, as you can see illustrated. Garbage collection is a way to reclaim memory from objects once they are no longer in use. Contrary to languages such as C++, Java has built-in facilities for automatic garbage collection. An object is eligible for garbage collection when it is no longer accessible through any variable. The finalize method is invoked just before an object is destroyed. Remember, this method is inherited from the object superclass, but you can override it to perform special actions before an object is destroyed. Let's illustrate this with an example. A person variable p1 is declared and initialized to a newly created person object with the name Adam. A second person variable p2 is declared and initialized to another newly created person object with the name Robert. The variable p1 is then reassigned to the reference object of p2. The person object with name Adam no longer has any references pointing to it, so it becomes eligible for garbage collection, as you can see illustrated. In this chapter, we zoomed into some advanced object-oriented programming concepts. After having introduced annotations, we discussed overloading methods, the disk keyword, and information hiding. We then elaborated on class inheritance, packages, and interfaces. The chapter was concluded by explaining the concept of garbage collection.